Beth, I have bad news. I'm quitting the show.
What?
I've decided to pursue my first love, magic. I am now going to be known as Martine the Great. And if you play your cards right, you can be my assistant.
Okay, Martine, what brought this on? Not that I don't love a good magic trick, but do you think you can make a living at this?
Well, I've learned that I can read minds, and not just one simple mind, but many minds.
I know I'm gonna regret this, but what brought this about?
Watch and learn. I am going to read your mind. What I need you to do right now is think of a number between 5 and 15. Think of that number, concentrate on that number, and send it to me through the internet, through the air, and I will read your mind. We're here at the National Air and Space Museum, and we're going to start at the welcome desk. You're going to take steps into the museums to the different artifacts. Count with me as I go. 1, 2, 3, 4, 5, 6, and so on. Think of your number. Now count. 1, 2, 3, 4, 5, and so on. Now look at where you've landed. Concentrate on that artifact. Think about that artifact and send it to me. Now what I want you to do is I want you to count the opposite direction, the same number of steps. So if you had 6, you would go back 6 steps. Count with me. 1, 2, 3, 4, and so on. Now look at where you've landed, somewhere around the museum. I know that you are not at the Ford Trimotor, and I know that you are not at the Wright Flyer. And I know that you are not at the Mercury capsule or the F-14. Now what I need you to do is take 4 more steps. This time you can move any direction you want. This way, this way. Count with me. 1, 2, 3, 4. Now look at where you've landed. I'm really going to concentrate and read your mind. Concentrate on the artifact that you're in front of. And I know that you are not at the Hubble Space Telescope. You're not at the Spirit of St. Louis or Alan Eustace's spacesuit. You're not at Sputnik. You're not at the Coast Guard helicopter. You are not at Spaceship One. Right now I know that you are at Neil Armstrong's spacesuit.
Well, it's pretty neat, Marty, but is it really magic or is it math?
We'll find out. This is STEM in 30.
Hi, I'm Beth.
And I'm the great Martine, and we are coming to you from the Smithsonian's National Air and Space Museum in Washington, D.C.
Today, our entire show is about the M in STEM, which is math.
We're also going to talk about the M in magic and mind reading. As a matter of fact, I'm going to read some minds right now and introduce to you Lillian and Nathaniel and Katie and Bowden and Elena and Taryn and Nyla. Ta-da!
You've been working with them for the last 20 minutes. You should probably know their names.
True, but the magic trick at the beginning was really good, right?
We're going to jump right into our show today, and we're going to introduce a very special guest who knows a lot about math. He's joining us via video.
He was drafted in 2001, is a 9-time NFL Pro Bowler, and plays the center of attention. Please welcome Toro, the mascot of the Houston Texans. Hey, Toro.
Toro? Thanks for joining us today, Toro.
Now, Toro, you've got some incredible videos that you've produced that connect what you're really good at, football, with math. Check them out.
was really awesome.
Toro, have you met any astronauts?
Toro, that is a great question. As a matter of fact, we got a chance to talk to astronaut Peggy Whitson, who made a mistake while she was 250 miles above the Earth.
Toro, thanks for joining us. Good luck on Sunday.
Thanks. I'm joined by NASA astronaut Peggy Whitson, two-time commander of the International Space Station. Peggy, thanks for talking with us.
Yeah, it's great to be here.
Tell us about math. You're an astronaut. Do you need to use math when you're in space?
Yeah, we do. We use math a lot. We count on the ground sometimes to tell us the specifics of a lot of activities that we're involved with. But we use math all the time. It's part of being there, I think. But it's not anything to be afraid of. I struggled with math in high school and in college, and it's all doable. You just have to keep practicing, and don't let failures set you back or keep you from trying even harder and being successful. Because at least for me, math was very intimidating, but you can overcome that. But even now, now and then there's mistakes that happen.
Did you ever make a mistake?
Oh yeah. On orbit, I was doing this experiment, and it was actually a really cool experiment where we were looking at a colloidal solution of iron and putting it in an electromagnetic field, and that solution would become solid. It was really cool, and it's potential future applications for earthquakes and suspension bridges and buildings, to increase tensile strength during an earthquake. But I had to put in dial in the electromagnetic field strength, and instead of 20 hertz, I put in 2.0 because I didn't see the decimal very well, but I made the mistake. And what happened then? They saw that instead of a solid, it formed this wave pattern. So it was actually kind of interesting that I didn't make a mistake, and they discovered something that they hadn't seen.
So you learned from that mistake.
Exactly. And the scientists went back and we repeated all the investigations at 2 hertz instead of the 20 hertz too. So it was a kind of one of those serendipitous errors. So don't be afraid of mistakes either. You can sometimes take advantage of them, but also always remember it's how you handle the mistakes that will make all the difference.
We are standing in front of a giant mural by Robert McCall.
How do you think that McCall got this huge painting up on the wall? Any ideas? Nyla?
Scaffolding?
He used scaffolding to paint it.
Good.
Yep.
Katie?
He could have started with a smaller image and then copied it.
That's exactly right. Robert McCall started with a much smaller image and enlarged it.
And what he had to do was, once he painted that image, the small image, he had to put it to scale. So he had to put a grid over it, and then he enlarged the grid and put it on the wall and painted it block by block.
Now, we recently got a chance to go to a school and do that exact same thing with a different painting with a group of kids. We're at Providence Elementary School, and we are joined by a bunch of young mathematicians, and more importantly today, artists.
And today, these mathematicians and artists are going to help us enlarge a painting by Alan Bean.
Now, as you can see, Alan Bean was an incredible painter, but something you might not know about him is he was the 4th person to ever walk on the moon.
The painting we'll be enlarging is called The Fabulous Photograph We Never Took. Do you guys want to hear the story behind this? Yes. Okay. When Alan Bean and Pete Conrad were on the moon, they had a timer for this camera, and the timer broke. And cameras back then, it was really hard to do a selfie. So what Alan Bean did was, when he got back from the moon, he imagined what that photograph would look like, and he painted it. And he used the boots that he used on the moon to press into the painting. He used patches. There's a little moon dust in here, so it's a really interesting painting.
So today you all are going to be creating scale drawings of this. So what we've done is we've divided it up into squares. Each one of you is going to get 1 square. You're going to scale that square up 900% to create a larger drawing. We're going to put all of those together and create a big scale drawing of this painting.
You guys ready to get started?
Yeah.
Let's go.
Together. Got it? Okay. And then you're going to do the same thing on that side.
Look at the whole painting. What do you notice up here?
Unfortunately, we've run out of time, but you all have done some really great work today.
And what's interesting, we've got a couple of our friends up here showing us their products, and they're not quite done yet, but look at the different approaches that they've used. You've taken more of a holistic approach, working on the whole picture, drawing lines across squares.
And over here, you've taken square by square by square, which is a little different, but I think it's going to be awesome.
I cannot wait to see what this looks like when we put it all together.
Well, as you saw, our friends at Providence did some really great work.
Unfortunately, they didn't get done that day, but I went back a couple days later and I picked up all of their finished pieces. Would you guys like to see what it looks like all put together?
Yeah.
Great, y'all have to build it.
Get to work.
Go!
This one?
Oh, there we go. That's looking better.
Boom! All right, well, let's tie all of this together. So we know that Alan Bean, who did this painting, walked on the moon. Well, when this mural was being done by Robert McCall, Alan Bean came into the museum one day. Alan Bean, being a painter himself, was talking to McCall and said, "Can I paint something?" And so McCall gave him a paintbrush and he went over and he painted something very special, and it's the only part of this mural that Robert McCall didn't paint. You guys want to see it?
Yes.
All right, come with me. So everybody look up, see if you can see anything. So see the big moon over here. Look around. And right now there's a shadow there, but look to the right of that and you're going to see a 5-point star. You saw it. Do you see the 5-point star? And it doesn't match anything else, does it? It's got the 3 rays coming off of it. Do you know what that is? That is the symbol for astronaut. And it was painted by an astronaut that walked on the moon. Speaking of astronauts,
And math, we got a chance to talk to an astronaut who helped me with some math problems that I used to have trouble with in middle school.
we are joined by NASA astronaut Joe Acaba, a veteran of 3 space flights. He spent over 300 days in space, and he was a teacher before becoming an astronaut. Joe, thanks for joining us.
My pleasure. Thanks for having me.
Joe, you taught math and science.
Yes.
I was not very good at algebra, but I think we have a demo that may have helped me. Marty, do you have some equations?
We're going to have 1g equals xc. The g stands for a glue stick, and the c stands for a paper clip, the x being our variable we don't know. So we're going to try to balance this equation now. So Joe, can you help us out a little
I
bit?
will.
1,
We need more than that.
11,
The pressure's on.
12.
And it
That's
looks like
good.
we're
All
balanced.
right.
So now we know that 1g equals 12c. 1 glue stick equals 12 paper clips. Now let's make that a little bit harder.
Go ahead and put that with a glue
With the
stick.
glue?
Yeah.
All right.
So now we have that 1G, the glue stick, plus 1P, the pen, equals 12 paper clips. We already know that that equals the glue stick. Now we're going to have to add in more paper clips. So that's our XC. So let's add a few more paper clips
Okay.
here.
All right.
1, 2, 3, 4, 5, 6, 7.
8. There we go.
And we're balanced. And so an algebraic equation is just balancing each side of it. So now we know that 1G plus 1P equals 12C plus 8C. So we've got 20 paper clips over here equaling these. And if we do a little bit of math and subtract, we have to take the same thing off of each side. So if we take the glue stick off of that side,
See ya.
now we're unbalanced. So we know that the glue stick equals 12 paper clips. So we have to take 12 paper clips off of this side. And now we see that our equation is balanced once again.
So, Joe, when I was in middle school, all I needed to know was that I just had to keep both sides balanced.
They always have to be balanced. Life's got to be balanced, and math's got to be balanced.
And that's why math is such an important part of a balanced education.
Ah, there you go.
On your mark. Get set. Go! Oh, here they come, here they come, here they come, here they come! Oh, what a great race! Wow, you guys are fast. Take a look at that. You all were incredible. Now we're going to go in here in a second and do a little bit of math and compare how fast you were to a very famous airplane. Come on. On December 17th, 1903, the Wright brothers, Orville and Wilbur, completed the first successful airplane flight.
To calculate the average speed of the first flight, you need to complete the equation speed equals distance over time.
The entire flight went 120 feet, and the airplane was in the air for 12 seconds. This means that we divide the 120 feet, the distance of the first flight, into 12 equal parts.
Each of these segments represents 1 second of time and how far the plane would travel in that second. When we do the division, 120 over 12, we see that each segment represents 10 feet.
This gives us an average speed for the first airplane flight of 10 feet per second. Our friend ran the 120 feet in 8 seconds. Putting these numbers into our equation, we see that speed equals 120 feet over or divided by 8 seconds, giving them an average speed of 15 feet per second. Based on these calculations, a middle school student is definitely faster than the Wright Flyer's average speed on the very first airplane flight.
You all were faster than the Wright Flyer.
Now, teachers, we want you to compare your class to the Wright Flyer. See how fast they are, run the race 120 feet, time them, calculate that average speed, and send us the results. We want to see if you all are faster than the very first airplane.
What can't you take on the very first airplane?
Luggage?
You're exactly right. There's no place for luggage. But how is math involved with luggage on an airplane?
With the holidays coming up, we've brought in Saffron engineer Corey Williams. Corey, come on in here. Corey, you've got some luggage here. What are you doing with it?
That's right, I have some luggage and I also brought an overhead stowage bin with me. So if you want to see how I solved a real world design problem using math, come follow me.
Cool.
Well, once again, you're going to be left.
Holding the bag.
Yep.
Well, off to Grandma's.
See you later.
Later.
All right, I'm going to show you how I use math every day in my job. So I'm a product development engineer. So what I do is I use math to predict how things are going to function before we actually have to build it. Because building things takes a lot of money and it takes a lot of time. But if you can figure it out with math beforehand, you can save yourself lots of money and lots of time. So that's what I did with this prototype here. The way it functions is you can fit more luggage inside of this overhead stowage bin, and it pivots up and out of the way of your head, so it doesn't take up as much space as other bins. But the issue with it is that you're putting a lot of weight inside that you have to push against. So that takes a lot of effort. So our design problem was we wanted to minimize the amount of effort that you needed to use to push this bin closed. In order to do that, I used what's called a free body diagram. So that's combining math equations with sketches. So what a force is you're putting energy into something. So center of gravity is the point where I can perfectly balance it without it falling over. The third is a pivot point. So if you think of a door, the pivot point on a door is at the hinges. Whenever you open and close it, everything rotates around the hinge. So on this pivot bin, that point is right here. The bucket rotates around this point. You can draw the force from the weight of the bucket directly at the center of gravity of the bucket. You can then measure between the center of gravity and the pivot point to get another variable. When you multiply those two together, you can put it into an equation up here that describes the bin opening. We want to keep this weight as low as possible because in a plane, it's really important to keep things light so it doesn't use as much fuel when it's flying. So I'm going to show you the material we use. So this is called a honeycomb composite panel. The outside white skins are glass fiber, so you weave them together into a skin, and then you glue them to a core that's mostly paper and air. So it's really strong and really light. So I'm going to pass this around to see if you can possibly break it. It's really hard to do.
When you use software, do you have to understand the math that it uses?
Yeah, when you're using software, it does a lot of the math for you, but the thing that you need to have is an intuition whether the answer you're getting is right or wrong, because there's a lot of places where a mistake could be made. So even if I'm just plugging numbers into software and I get an answer, I need to have a feeling for if that's correct or not. Yeah, so there are a lot of times where I'll get something and I'll notice it doesn't look quite right, and I'll go back in and I'll find a mistake and I'll fix it. So if you practice a lot and you do a lot of math, you build that intuition, and it helps you even when you are using software that does it for you.
Ladies and gentlemen, the sound you just heard was a note, also known as a sound wave. Please make sure your seat backs and tray tables are in the full upright position, and prepare to learn about the connections between math and music.
I'm Doc Nix. I'm the director of the Green Machine at George Mason University. Musical notes are tones. Tones are sound waves that have a specific frequency. Frequency describes the number of waves that pass a fixed place in a given amount of time. Listen to this note. This is the note's sound wave. In 1 second, sound moves 1,100 feet. Frequency measures the number of waves that happen in that space. The fewer the waves, the lower the frequency, the lower the note. The more waves, the higher the frequency, the higher the note. We have been playing with notes and harmonies for most of human history. Harmony is when two or more notes sound good together. But most tones don't sound good together. Getting two instruments in tune with each other was a big challenge. Way back in the day, if I made an instrument and you made an instrument, the note you call A and the note that I call A probably didn't match. So people got together to agree on standard notes. The note known as A was fixed to a frequency of 440 hertz. And then all the other notes on the 12-tone scale were based on that note. Today, that standard is known as A440. All the instruments you know are designed to be fixed to this standard. An interesting math fact about musical frequencies is that if you double the frequency of a note, you get the octave of that note. This occurs naturally. This isn't something human beings made up. If you start with A440 and then play the same note up 1 octave, that's A880. Next A up is 1760. Next A is 3520. Melody and harmony combine into a complex mathematical web of frequencies, making beautiful music together.
You all did a great job today, and I hope you learned a little bit about math.
And now we're going to learn a little bit about magic. As a matter of fact, I'm going to teach you guys how I did the magic trick at the beginning of the show using a little bit of magic.
And a whole lot of math.
If you were amazed by that magic trick, I have a little secret for you. It actually wasn't magic, it was math, and I'm going to show you how this trick works. When I had you choose a number between 5 and 15, really all I needed you to get past here to begin with and count around the circle. And it didn't matter what number you chose. So if you chose 7, 1, 2, 3, 4, 5, 6, 7, you landed somewhere around the circle. But then I did this and I took off 2 pieces, the first 2 steps. And by doing that, no matter what number you chose to begin with, when you counted back that same number, you were always going to end up at the Spirit of St. Louis. Look, 1, 2, 3, 4, 5, 6, 7. Once I knew that everyone was at the Spirit of St. Louis, I started removing pieces. So I removed the Wright Flyer, the Trimotor, the Mercury capsule, and the F-14. And what that did was, I allowed you to have choice, 4 spaces. You could go any direction you want, so it seems like you're in control. But are you? If I know you're here and you're going to move 4 spaces, look what happens. 1, 2, 3, 4. You end up at Neil Armstrong's spacesuit. If you count the other way from the Spirit of St. Louis, 1, 2, 3, 4. I know that you're at Neil Armstrong's spacesuit. So no matter what number you chose to start with, because of me removing these 2 pieces, it became a simple math counting trick. So was it magic? Nope, just a little bit of math. Well, are you ready?
What?
You have done a great job today. You are ready to be my magician's assistant. As a matter of fact, we're going to start by cutting you in half to learn about fractions.
I have a better idea. Let's learn about subtraction by making you disappear.
Where is he? He just poof.
Well, I made him disappear before I got to thank everybody. Do you guys want to help me thank everyone? Sure. We'll start by thanking Saffron for sponsoring our show today.
And many thanks to all our experts and guests.
Special thanks to Corey for bringing his luggage bin all the way from California.
And be sure to check out Toro's math drills. You can find the link on our Facebook page.
And if you have any more questions for us, join us and our expert on December 18th at 1 o'clock for our Facebook Live Q&A.
All right, thanks for watching. Great job today, and I hope you learned a little bit about math.
Now you're going to learn a little bit about magic, as a matter of fact.
Let's learn about subtraction by making you